Okay, hello everyone, welcome. This is the second webinar of our spring series. Today I have the great pleasure of hosting this webinar with Célia Fonseca Guerra, who is a full professor at the Vrije Universiteit. Do I say it correctly? More or less. She is at the Applied Theoretical Chemistry and Supramolecular Quantum Biochemistry department. She's one of the original ADF developers, and she worked on the parallelization of ADF as well. And currently in her group, she focuses on weak interaction, bonding in supramolecular systems. And today she's gonna talk about the energy decomposition analysis method that we have implemented in IMS. And with that, Célia, the floor is yours whenever you want to start.
Well, thank you very much, Maria, and thank you all for joining. So I'm going to talk today about hydrogen bonding, and I'm going to focus particularly on the energy decomposition analysis. And I want to show you all the unique aspects of hydrogen bonding. So what, let me go to, to the next slide. So what are actually hydrogen bonds? So if we think of hydrogen bonds, we see them normally as an interaction between a positively charged hydrogen atom and a negatively charged oxygen atom. So this is the way we learn in our bachelors of chemistry how this weak interaction works. But today I want to show you by applying the energy decomposition analysis together with Cauchy molecular orbital theory, so the combination of the two, we will understand that these hydrogen bondings are actually very interesting and have unique phenomena. So it will start with the method that I've used. So of course, here in Amsterdam, we use the Amsterdam density functional program, which is a DFT-based program. So for those who want to know, the functionals that I normally use in this work is the B-lib functional with the Grimer correction, the D3 Beck-Johnson. And in the older work, so before the Grimer correction, a lot of things have been done with BP86, and BP86 is quite a good functional also for hydrogen bonding. A TZ2B basis set, and most of the work which I show here is in the gas phase. But now about the energy decomposition analysis. So here the QR code refers you to the tutorial of on the SCM website, where they explain very how you do these sort of computations. I will focus more on the research. So how do you do research with the energy decomposition analysis? So you start, in the case of hydrogen bonding, with two monomers. When these two monomers come together, they form a complex and they deform for that. So you will have a strain, so the deformation energy. And then these two monomers can interact, so they can form hydrogen bonds, and that is the interaction energy. These two terms together, they make up the bonding. And this interaction energy can be decomposed into different terms. So that is the electrostatic interaction, which is just the attraction between the two unperturbed charge densities of the monomers between the electrons and the nuclei. You have the Pauli term, which is for obeying the Pauli principle, so the repulsion, destabilizing interaction between the occupied orbitals. And you have an attractive term of the orbital interactions, which in this case for hydrogen bonding, it's mainly donor-acceptor interactions. I will come to that later. And also polarization within one of the monomers due to the presence of the other monomer. And in the newer work, there's also a term for the dispersion. But in the case of hydrogen bonding, it's in this case not so important. So how this work started. The energy decomposition analysis was implemented in the ADF software code already in the 80s. And one of the things that we wanted to understand with the energy decomposition analysis is why are the hydrogen bonding in DNA base pairs so strong? And people had the idea that it's because of resonance assistance. So the pi electrons, they polarize and they just make these hydrogen bonds stronger. So by doing the energy decomposition analysis, you can retrieve the reason for having these strong hydrogen bonds. So we computed the bond energy between adenine and thymine, minus 13 kcal per mole, between guanine and cytosine, minus 26.5 kcal per mole. Now, the deformation energy, the strain is small, 2.3 and 4.1, and you have an interaction energy of minus 15 for AT and minus 30 for GC. These can be decomposed in different terms, so in a Pauli repulsion, in an electrostatic interaction, and in an orbital interaction. And what is very important here to notice is that these hydrogen bonds are not only electrostatic interaction. There is a large component of minus 22.4 of orbital interaction and minus 34.1 for guanine cytosine kcal per mole. So we then decompose this into two terms, in sigma electrons and pi electrons. So due to the symmetry of the AT and GC base pairs, they have CS symmetry, you can decompose in sigma and pi electrons. And what we saw is that the large orbital interaction comes from the sigma, so minus 20.7 and minus 29.3. So what we can say already is that the important factor here for having a stabilizing orbital interaction is not the resonance assistant, it's what we thought probably donor-acceptor interactions. And actually what we found, and I will show it for the GC base pair, is that there are stabilizing donor-acceptor interaction between the lone pairs, for instance, of the oxygen atom here of guanine, donating electronic density towards the NH2 group on the other side. And you also have the other way around, the lone pair on the oxygen of cytosine and the lone pair on the nitrogen of cytosine donating charge into the NH anti-bonding orbitals on guanine. So now we proved that there was donor-acceptor interactions with the energy decomposition analysis, with a Cauchy molecular orbital diagram, but we went one step further. We also wanted to see how the density flows due to the hydrogen bonding. And for that, we used developed the Voronoi deformation density analysis. And what we do, and I have here as an example pyridine, we start from spherical atoms. And when we turn on, we do an SCF computation, you get the final density. So you go from the sum over spherical atoms, you go to the density of the molecule. And if you analyze this density by integrating over the Voronoi cell of atom A, so that's the space that is closest to that atom A and not to any other atom, and you integrate over that space, and you do the have the density of the molecule, so minus the the sum over the spherical densities of the atoms, you can see whether there flows charge towards atom A. So if it's smaller than 0, atom A gains electrons, and if it's larger than 0, then atom A loses electrons. And this can also be divided into sigma and a pi component. So when we do that, we can actually see that by analyzing the Voronoi deformation density changes, that the oxygen atom loses density. So there is indeed a lone pair donating charge towards the anti-bonding orbital on the other fragment. And here we have the NH2 group gaining electronic density in the sigma system. And the pi systems shows also polarization. So what we see here is that the oxygen atom gains electronic density in the pi system, and the NH2 group loses density. And also for the other hydrogen bond, we see a similar effect, that the nitrogen gains density in the pi system and loses density in the sigma system, due to, in the sigma system, we have the donor-acceptor interactions. So what do we know now for hydrogen bonding? So the nature of hydrogen bonding. So our first work that we did on hydrogen bonding with the energy decomposition analysis, we saw that there is electrostatic interaction, which we confirmed, that there is charge transfer interaction from the lone pair of an oxygen or a nitrogen atom towards an accepting orbital, an unoccupied orbital on the NH group, that there is steric repulsion, dispersion is there. There is also cooperativity. So when you donate from one side, do not have a charge accumulation on one monomer, they become stronger, these hydrogen bonds, and you have pi resonance. So quite a lot, and this inspired us to do research on different aspects due to this complex nature of the hydrogen bonding. So what we did, we investigated cooperativity. I will show you that steric repulsion, so the Pauli principle, can also be the reason why a certain dimer has stronger bonds than in another dimer. I will show you that we explained for the first time how the secondary electrostatic interaction works. So it's a model that is widely used in supramolecular chemistry. And I will show you why urea and Thiourea differ in hydrogen bond strength. And I will start with the first one. So the cooperativity. This research was done by Dr. Lucas de Azevedo Santos and Dr. Pascal Vermeer. And they have worked on cooperativity of squaramides. So squaramides can form linear chains in supramolecular chemistry. And we will first focus on the geometry. So the first thing to do always when you do some theoretical research is to focus on the energy and the structure. So what we did is we computed this chain, and what we analyzed is how the monomer changes in that chain. So what we look first, so indeed, we look here at the NH group, and we see that it goes from 1.01 angstrom towards 1.04 angstrom. So it expands. Also, the CO bond length becomes longer. So the NH becomes longer because it accepts electronic density in the sigma star, and this one becomes longer because it donates density through the lone pair, which is also partially localized on the CO bond. And what we also saw further is that the square becomes more regular. And I will talk also about this equalization because in the it's thought that this is due to aromaticity. But I will show you that we can have a very precise explanation why the ring becomes more equal. So the first thing to do is to see whether there is cooperativity or not. So if we divide the interaction in energy by the number of interaction points in a chain, so n-1, we see that it becomes gradually stronger as the chain increases. So now I will try to show you where this increase comes from. So we define for that reason the synergy, and what we do is we define the synergy as the interaction of the chain minus the n-1, so just divided by the number of interaction points, and we subtract from that the energy of the dimer. So if there's a lot of synergy, this term should be much larger than the interaction energy of the dimer. So what we see, if we gradually increase it, is that the synergy becomes stronger with the number of monomers. So a chain of 4 has a much larger synergy than a chain of 3. And what we also see is that it comes with the electrostatic interaction and with the orbital interaction. And this orbital interaction shows us a synergy in the pi system and a synergy in the sigma system. So now we have the numbers, and we know that we have to look for the reason in the electrostatic part and in the orbital interaction part. So what we now are going to look for is the origin of the cooperativity. So on one side you have the hydrogen bond donor, and on the other side we have the hydrogen bond acceptor. We know that when you have a dimer, there is charge flow from the lone pair of the oxygens towards the NH2 groups of the other monomer. So this one will become slightly negatively charged, and the other monomer will become slightly positively charged. And if you do that for a longer chain, this becomes larger. And what you will see is that gradually you will have here a negatively charged squaramide, and on this other side a positively charged squaramide. And adding a new one will just have an enhanced hydrogen bonding. So we explained the cooperativity, but we have not explained the ring equalization yet. And this we found very interesting because due to the hydrogen bonding, we saw that the ring becomes more equal. So you see, for instance, this distance here between these two carbon atoms goes from 1.57 to 1.51. And the other one elongates 1.40, goes to 1.43. So we wanted to understand why this happens. And what we did is we analyzed the squaramide by optimizing it and making gradually the CO distance longer. So by making the CO distance longer, we saw that the change is not so much in the C3, C4, also not in the C1, C4, so the two blue ones, and also not in the C1, C2. So what we see here is that that the C1, the C1, C2 is the one that reacts most to the CO elongation. So we took this part of the system and we elongated the CO bond, And we looked what happened to the CC. So if you elongate the CO bond, the two carbon atoms can come closer together. So this is the reaction, what happens. Now we wanted to analyze what is the reason behind that. So why do these two carbon atoms can come closer together when the two COs elongate? And what we saw is that the interaction energy goes down when the CO elongates, and that is not due to the electrostatics, because that becomes less, but it's really because of the Pauli repulsion becoming less. And what we saw there is that when you elongate the CO, the two occupied orbitals of the sigma HOMO will have a smaller overlap. So here is a picture where you can see that. So the CO bond will have less amplitude on the carbon, and therefore there will be less repulsion. So what we know from cooperativity in hydrogen bond and X bonds is that this cooperativity is due to the charge separation in the sigma system, the covalent component actually of the H bond and the X bonds, and the equalization of the Squaramide is due to the CO lengthening. So we can really pinpoint that it's due to having their Pauli repulsion. The next thing I want to show you is about the difference between GG and CC. So guanine-guanine dimer and the cytosine-cytosine dimer. Guanine-guanine is stronger bound than the CC one, and I will show you that this is due to steric repulsion. This work done by Dr. Stephanie van der Lubbe. And for that, we go to these systems. We have here the cytosine and guanine, and in the smaller ones, the C prime and in the G prime dimer, what we have done is we have taken away the oxygen here. So to be sure, we have really only two hydrogen bonds, nothing intervening. And here the NH2 group has also been taken away. So the proof for all four is that GG and G prime is stronger bound due to having less Pauli repulsion. So what we did, we of course optimized these systems, computed the bond energy and the interaction energy, and what we see is CC has a smaller interaction energy than GG, but has also longer bonds than GG. So if you then do the energy decomposition analysis with these distances, you will always find that the system with shorter bonds will have larger components. So what we see here, GG has larger electrostatics, more Pauli, more orbital interaction. So you cannot explain the difference of CC and GG from that. Now, what I will show you is that what you need to do is use the activation strain model. So this model was developed by Bickelhaupt for reactivity, but it applies also for minima, because these are also like the same way they depend on the slope of the components. So the activation strain model tells you to look at the slope of the electrostatic interaction, of the Pauli repulsion, and of the orbital interaction. And that's what we did here. We started from the minima, and what we did, we varied the distance. By varying the distance, we see that everywhere GG is always stronger bound. And now, if we do the decomposition, we find the reason why. So the electrostatic is more or less the same for both systems. the orbital interaction also the same, but the Pauli repulsion differs. Of course, we anticipated that it might be that people would say, you have here an oxygen atom and here you have an NH2 group that do not matter. So we also did the same analysis for C prime and for G prime, and the same results appeared with energy of -15 and -25. So in view of time, I skipped the energy decomposition analysis, but in the paper of the chemistry 2017, you will see that it has exactly the same results, showing that the Pauli repulsion is the most important one. And what we saw is that the largest overlap of CC is always twice as large as the one of the GG. So what you can see here is the red one is the overlap between the nitrogen lone pair with interacting with the orbitals on the other side of on the NH group, and by being more directional than the lone pair on the oxygen, you will see that you will have more overlap of occupied orbitals and therefore more Pauli repulsion. So what we have here is an enhanced stability of GG that is determined by having just less Pauli repulsion, and in the other case, the Pauli repulsion is responsible for the enlarged hydrogen bond distances in CC, and therefore weakening also the electrostatic and the orbital interaction. This is a factor that has been overlooked by now in the literature as one of the reasons why certain hydrogen bonded systems are stronger than other ones. So let me now go to the third one. So I have shown you that how the donor-acceptor interactions are important for cooperativity, that Pauli repulsion can determine differences in hydrogen bond energy. And now I will show you that our energy decomposition analysis was able to show why actually this secondary electrostatic interaction model works. So this paper, the first paper was published in JACS in 1919 by Jorgensen, and what he showed is that two systems can be explained with the SAE model. Well, this work, I will show you here the reasoning behind the secondary electrostatic interaction model. What they say is you have GC with an energy of -22.1 kcal per mole. So these are the data from the paper by Jorgensen, and PU has an energy of 11.4. What they said is the reason is this difference comes from the diagonal terms. So they, if you would take that all the terms, all hydrogen bonds are the same, and you would say you have here repulsive diagonal terms, and here you have attractive diagonal terms, and this one only has repulsive diagonal terms. So the secondary interaction are the attractive or repulsive, and how that is explained is you have two situations. You can have either the donor atoms on one side and all the acceptor atoms on the other side, and then you have diagonal stabilizing interactions, but you can also have that they are opposite to each other, and then you have destabilizing interactions. And these are all 2 to 3 kcal per mole. By now, this is standard teaching material in physical organic chemistry and supramolecular chemistry. But notice, this is an hypothesis, and it is not proven by any bonding analysis. So what we did is we went to model systems. We have two systems almost the same. The only difference is the location of this proton. And what we have here in the DAAA system is that you have net attractive interactions, and the DADA system has net repulsive interactions. So the DDAA has an interaction energy of almost -72 kcal per mole, and the DADA has an interaction energy of -33 kcal per mole. So we wanted to understand where this comes from. And what we did is analyze this with the energy decomposition analysis. But before doing that, I want that you see that the green one, DDAA, has much shorter hydrogen bonds than the DADA. So if you do an energy decomposition analysis on these systems, you will find that all the terms are larger for the green one, for DDAA, because it has shorter distances. So this will not explain anything to you. What you need to do here is use the activation strain model to understand this. So you vary the distance between the two monomers. And by doing that, you will see that the interaction energy is always larger for the green one, as expected. And then you can verify which term is the most important one. So the electrostatic interaction shows us that the DDAA, so this one, has a stronger electrostatic interaction. We see also that the Pauli repulsion is not different. So this one does not explain the difference in energy. And the orbital interaction is also larger for the DDAA. So now we go to the explanation of this. If we look at the electrostatic interactions, and here I have a plot, you see that the DDAA has more negative charge here on this side and more positive charge on that side. This is, however, more uniform. So there will be a larger electrostatic interaction when this one pairs, the DAAA, than when the DADA pairs. And this can be made even more visible by looking at the Voronoi deformation density. So if I sum up the upper part of this of the DDAA, I see that I have here a positively charged upper part and a negatively charged lower part. So this part of the molecule, when it pairs with another one, will have a stronger electrostatic interaction, whereas the other one does not have that so much. And this has a direct impact also on the level of the orbitals. So if we compare the orbitals of the DADA for the similar hydrogen bonds, so for now, first we start with the lower one, the oxygen with the NH, and what we see is that for the DAAA, the lone pair is higher in energy because the molecule is there slightly negatively charged, and the LUMO is lower in energy because it is slightly positively charged on that side. And the same holds for the other hydrogen bond. So for the nitrogen atom, what we see here is that the lone pair goes also up in energy, and the accepting orbital goes down in energy. So this explains the better orbital interactions in these systems. But now, of course, I have to go back to the original GC and PU systems. What do we have here? GC, these are our computations. So it's GC amounts to -33.7 kcal per mole. So this is with the BLibD3 functional, and PU to -21.5. Indeed, this one is stronger bound. If we look at the different terms, we have a similar result as in the previous case. The electrostatic is stronger for GC, and also the orbital interaction is stronger. And if we want to explain that, just by looking at the map, you see that here you have some sort of charge accumulation, charge depletion, resulting in better electrostatic interaction, also with cytosine. You see here charge accumulation. So what does this secondary electrostatic interaction model actually do? So why does it work? It works because it is in some way, it tells you about the grouping of the hydrogen bond donors and acceptors. And therefore you can have accumulation of charge around the frontier atoms. And this enhances then the electrostatic interaction and the orbital interaction. So counting the number of secondary electrostatic interaction gives you an indication for where the charge accumulation is, and the SAE model can predict hydrogen bond strength, but the right answer, but due to an incorrect explanation. So only the energy decomposition analysis together with Kohn-Sham molecular orbital theory and the VDD analysis could give us the answer why this SAE model works so well in supramolecular chemistry. So let me now go to the last one. So urea versus thiourea. And this work was done by Celine Nieuwland, published in Chemistry. And what we wanted to understand is about thiourea, hydrogen bonded systems. So what these thiourea are used in organic catalysis because they have stronger hydrogen bonds. The explanation for now is that that this enhanced hydrogen bonding comes from the difference between oxygen, sulfur, and selenium. So it cannot be explained due to the electronegativity. So what they say, the hypothesis is that in sulfur and selenium, you have more polarizability in the bigger atoms. So we wanted to understand this, and we took model systems. So we have here urea with formaldehyde and an amide with also formaldehyde. And we see indeed that if you go to sulfur and selenium, the hydrogen bond interaction becomes stronger. And the hydrogen bond length also becomes shorter for selenium. So we did an energy decomposition analysis to see the terms, and indeed they are all stronger for selenium than for oxygen, and the same holds for the amide. So we went to try to understand this. So why the electrostatic interaction is stronger in this case? And by analyzing the Voronoi charges, we saw that selenium has an NH2 group that is more positively charged. And the same holds also for the amide. So having this more positively charged NH2 group will, of course, give better electrostatic interaction. And the other thing, what we also see then, is you have enhanced orbital interactions because this positively charged NH2 group for sulfur and selenium will have a lower LUMO. So then you will have better donor-acceptor interactions with sulfur and with selenium system because the NH2 groups have an accepting orbital that is lower in energy. So the LUMO of selenium is lower than the LUMO of oxygen. And for the other system, we found the same. For the amide, you have only one hydrogen bond. And there you see this similar situation that for oxygen, you have the higher lying LUMO, and selenium has the lower lying LUMO on the NH2 group. So we know now, and we focus now on amide, that the NH2 group is more positive. But why? So what we do now is we cut this bond. You can do that with the fragment analysis, and we used the formulation of the Voronoi charges which allows us to work instead of spherical atoms, we start from the fragments. So you have a fragment, an NH2 fragment, and you have here a fragment with a chalcogen and a CH. And we let this bond form. What we see when we do that is by looking how the charge flows, is that the NH2 group becomes more positively charged, going from oxygen to selenium. And this method allows us to see where it's located. So you can have a decomposition in the sigma and in the pi. And what we see here is that in the sigma system, there's not of much difference. And in the pi system, we see that going from oxygen to sulfur to selenium, the NH2 group becomes more positive in the pi system. So we have to focus on the pi system to reveal the reason why this hydrogen bonds are better for selenium. So what we did is we made the cone-sham molecular orbital diagram between by forming the bond between the NH2 group and the carbon chalcogen with a hydrogen atom here. So we have two fragments. You also form the sigma bond, but as this does not lead to charge depletion differences on the NH2 group, we do not focus on that. We focus only on the pi system. And we have the lone pair on the nitrogen atom that can donate electronic density towards the pi star of the CO. So when we show this also for sulfur and for selenium, we see that the same happens. And in our program, you can see how much of a charge, so how many electrons actually are in the lone pair after the bond formation. So after the bond formation, there is charge going to the CO, almost 0.3 electrons. And for sulfur, it's even more than 0.3. And for selenium is 0.35. So by having a lower lying pi star on the carbon chalcogen bond, more electrons can be donated from the lone pair towards the pi star. But why is this one lower? So why is the carbon selenium lower than the carbon oxygen? So what we did now is going for the next step. So we have now understood that the NH2 group is more positively charged for selenium than for oxygen, and that is due to the fact that more charge is donated from the lone pair of nitrogen towards the pi star on the carbon chalcogen bond. So this is now our next focus. We construct, we take a very simple system, an aldehyde, and we make the bond between the carbon and the oxygen, so the chalcogen. And that gives us that the stronger interaction is for oxygen than for sulfur and selenium, which are more or less the same. This follows the trend of overlap. So the pi electron pair bond stabilization goes as is the largest for oxygen, leading to the highest pi star. And this is fully determined by the overlap. So the overlap between the carbon 2p and the p orbital on the chalcogen is larger for oxygen than for sulfur and selenium. But of course you will say then, yeah, but selenium has a longer bond with carbon, and that is indeed the case. This one has a carbon selenium bond is longer, but why is that? So what we did is now we computed all these terms at the three differences, at the distance of oxygen, at the distance of sulfur, and at the distance of selenium. So here you have the graph for the overlap. So this is the overlap at the oxygen distance. This is sulfur, and this is selenium. So what you see here is if selenium would be allowed to be as close as oxygen, then it would have a larger overlap. And here are the pi stars, which show that if selenium would be able to come close to carbon, then it would also have a higher lying pi star. But it's not the case. And why is that? So here you can see it. All the terms, the electrostatic orbital interaction and dispersion, want selenium to be closer to carbon, because this is the lowest value you can find. But it's really the Pauli repulsion which does not allow selenium and sulfur to come that close to the carbon atom. So what we can conclude now is the atom size, so having a larger atom gives a longer CX distance. And because of that, you have the largest overlap between the 2p of carbon and the p orbital of oxygen. This results in a more destabilized CO pi star than for sulfur and selenium. And therefore, the NH2 group can donate more electronic density to the pi star of selenium, leading to the largest positive charge on the NH2 group. So now what we see here, due to the larger positive charge, you have a stronger hydrogen bond because of orbital interaction and electrostatic interaction. And what we can then conclude is that the hydrogen bond donor capability of carboxyl thioumides and selenoamides is dictated by the steric size of the chalcogen atom. So my take-home message to you. I've shown you that hydrogen bonds display a complex bonding mechanism. So here you have a picture where you saw all the terms that can be important. And these are revealed by the energy decomposition analysis, but not only by these numbers, it's together with the cone-shell molecular orbital diagrams and the Voronoi deformation density analysis. Well, before ending, I want to invite you to the ESOR 2023 in Amsterdam. So we have in our university the 19th European Symposium of Organic Chemistry with Nobel laureate Ben Veringa and many other very interesting speakers. And it will be at the O2 building of the Vrije Universiteit. It's a very nice building, very nice auditorium, and you will have a chance to get to visit Amsterdam. Now, I want to thank some people. I want to thank the whole TheoChem group for the very nice collaboration, all the PhD students that have contributed to this work, NWO for funding, and I would like to thank you for your kind attention. Thank you.
Thank you very much, Celia, for the very nice and informative talk. And we have time for some questions if there is someone that wants to ask something. We have a couple of minutes. Meanwhile, some questions come. I will ask you, Celia, can we have the slides?
Yeah. Which number do you want?
If we could have the full presentation, we could, in the website, we are.
Yeah.
Also, maybe here, I don't know if you can, in the handouts, if you have access in the handouts to attach the presentation.
No, I don't have that, no.
Okay, well, anyway, yeah, if you can send it to me in PDF.
Yeah, sure.
Great.
I will do that.
Okay, thank you. I don't see any question coming. So,
Maria,
uh-huh.
there's
Yes?
a question in the questions panel.
Okay,
It says, thanks for the talk.
Yeah.
I have a question. How does the BSSE basis set superposition errors have been included in the dimer calculations?
So we have done, and that is in the work, in my work already in '99, and it's actually in the JAX paper of 2000. We have computed the basis set superposition error, and that's very small. It's around 1 kcal per mole. But notice that for the explanations that I have given here, it will not change any of the conclusions. So, and I think that's important to notice that for all the concepts that I've shown, so hydrogen bond differences due to polar repulsion, the donor acceptor interactions in the cooperativity, it will not change. Yeah.
Okay, thank you. Yes, and now I see. Yeah, we don't have more questions right now. So, okay, thank you very much, Celia, for the nice talk. And please, everyone, sign up for the next webinar that we have in 2 weeks with one of our founders, Jan Barendens, who will talk about excitation energy calculations with nearly exact constant potentials. You will receive in a follow-up email an invitation to sign up. So please do that. And again, thank you very much, Celia, for the very nice webinar.
I think there are 2 more questions.
Oh, now they are coming more. Okay, we have, yeah, a couple of minutes. Okay, so with the last 2 works about the secondary electrostatic interaction potential and role of the chalcogen, would you expect the SEIP hold up if you change the oxygen for sulfur?
If I understood correctly, the question is if the secondary electrostatic interaction model holds if we would change the oxygen in a sulfur.
Yes.
I think so, but the effects would be a little bit less pronounced. Yeah. Because it does not have such a large charge as oxygen. Yeah. Okay.
Okay, yeah, we have another question. My question is if this type of analysis can be done for intermolecular systems.
Well, for doing the energy decomposition analysis, you need to have 2 fragments. We have done some work on that with intramolecular resonance-assisted hydrogen bonding, but it's more it's a little bit more difficult than when you have very clear 2 monomers. Yeah.
Okay, any more questions? People are thanking you. Thank you for this very didactic presentation.
I would like to thank also the people for their kind questions and for listening.